Okay, guys. Can you all hear me again? Okay. So the second half of today's lecture is going to be a little bit different. We're going to talk about base rule, and we're going to talk about radionuclide processes. And this is tomorrow's TA session is going to have quite a bit to do with what we're talking about, what we'll be following here in the next couple of, well, I guess hour and a half. So what's coming up now will be base, and it'll be these radon nicotine processes. Just to give you some heads up. So base rule, there are problems posted. So see additional problems on Canvas. I'm going to do one of them in just a second. Radionuclide processes, this is 3.1. There's a chapter, there's some pages in the thin textbook that we're going to be using. So we're down here in 3.1 and 3.2. So again, you can see the word state processes. It's called state prices, state processes, and state prices. They are often used. They're not quite the same, but yeah, related. So 3.1, this is section 3.1 plus 3.2. But what is to note is that we're actually also going to do something in 3.2. And in 3.2, it's a little bit hard to find. It's hidden over in his. You see, here's the radionuclide derivative. We talked about that quite a bit. It's over here in section 5.2. There are a couple of lemmas that I will call base formula that we're going to be needing over here. So there are a couple of lemmas. There are so this here was section, and so here we'll have lemmas 5.2.1 plus 5.2.2. We're going to be needing those. So we're going to start out with base rule, and I'm fairly convinced that everybody has seen something about base rule before. So it's a base rule. Base rule from intro probability. It'll say something like, well, I will compute P of A given B. I can do that, right? I can do that by the definition of the conditional expectation of A given B. This is going to be the probability of A intersection with B and divided by P of B. Right, now of course I have the identical formula if I switch B and A. This will be by definition P of A given B, but now we divide by P of B. Right, so provided that A and B have positive probability, I'll get this. And so you can see here that I can relate one to the other. I can relate one to the other simply by, well, I'll get here that P of A intersection B will be P of A and then times P of B given A. So now I have an expression for the intersection, and I can plug that into the first formula. This is P of B. And then up here I'll have P of B given A times P of A. Right, so this is often called base formula. Right, so when I was planning this lecture here, I was like, we get down to base formula, we should do something about it, in particular in this day and age. So let me just as I said, there are some additional problems up on Canvas. So let me just show you these additional problems. So if you go to Canvas, put it, forget where I put it, maybe on the modules. Yeah, base problems. So you pull this PDF file from base problems. And these are very elementary problems that involves base formula. The one that I wanted to do, and the reason I want to do it is, of course, because we have this pandemic going on. And so the problem that I wanted to do is this number 4. So let me try to write down what problem number 4 is about on the document camera, right? So it's this one here I'm interested in. So we do an example, and I want to do this particular problem number 4. Okay, so this is how. So the pandemic is going on in the U.S. and there are, and then in the rest of the world, of course. One thing you don't hear discussed, I don't think I've heard it ever discussed by journalists, is base rule. But if you go to the doctor and get tested, and you ask the doctor about base rule, the doctor knows full well what base rule is about when it comes to testing. And this example here is just, I'm not claiming these numbers here are calibrated in any possible way. It just gives you some idea about what base rule means in the context of being tested for a disease, right? So here's the example. I just picked more or less random numbers. So it's a test for a disease. So think about this as COVID. It is it's 90% correct if the patient is sick. It's also 90% correct if the patient is well. And then you know that 1% of the population has the disease. So is this a good test or is this not a good test? There's a lot, at least in the US, but probably all over the world, there's a lot of discussion about like vaccines, how good should a vaccine be before we would release it to the public? How good should a test be before we can consider it reliable? So here are some numbers, like specific numbers. So 90% correct if you're sick, right? So it'll tell you that you're sick. If you're sick 90% of the time, it will tell you that you're well. If you're well 90% of the time, and then you know the 1% of the population is sick. This is a good test. And these are the numbers that are being discussed. These are the numbers that are being discussed in the public. And so where in this discussion should base come in? Well, what you want to know is, what we want to know is, what is the probability that you're sick? So the patient is sick given that the test is positive. Like if you don't take the test, then the unconditional probability is that 1% is sick. So now we take the test, say the test comes back positive. Now we want to know what is the probability that you're actually sick. That's the calculation that we want to do if you want to answer this. This is again, I mean, the connection to our class is this flow of information, right? So before the test, right, then you only have unconditional. The unconditional probability is 1%, right? Then you take the test. So after the test, now you have a conditional probability. Conditional probability given that the test is positive. This is what we don't know. Right, so before you took the test, there was a 1% probability of you being sick from this disease. Now, conditional probability, what is it now after you tested positive? So again, you see there's a flow of information. Right? There's a before, then you get a piece of information, and now you'll readjust your probabilities. So what is it in this particular example? Well, let's just plug in numbers. This is, the numbers are not difficult to plug in. We'll use Bayes' rule. Like, you're always given the opposite of what you need. that's the rule of thumb, right? So we're going to use Bayes' rule, and that's, to answer this question, we'll use Bayes. So the probability that the patient is sick given that the test is positive, we'll use Bayes' rule. Right, so by definition, what is this? So that's the definition. This is the probability that you are sick. Patient sick and positive test. Right, conditional, so we have to divide by the probability of a positive test. And so here comes Bayes' rule. So this here is Bayes. But you can flip these two and compute this as P of positive test, given that the patient is sick. And then we have to multiply onto that probability. We have to multiply onto that probability times the probability that the patient is sick. And then divide by probability of a positive test. So that was Bayes' rule. Okay, so this is what you're given, right? That was a 90% probability. That was a 90% probability, and you're interested in the other one, right? So of course you can break the bottom part in, right? I can use here that if I'm looking at the set of a positive test, I can write this as what? I can write this as positive test, and then I can intersect with patient sick, and then I can take a union, positive test, intersection with patient well. So if I can work out what the bottom part then is using these conditional probabilities. So I can write this here as the probability of a positive test given the patient is sick times probability of being sick, and then I divide here by, instead of this probability, I'll take the probability of these two. So I'll take here the probability of a positive test given that the patient is sick times the probability of being sick. plus, so this is all going together, probability of a positive test, given that the patient is well, times the probability of being well. So now I have all the numbers that I need. I'll just plug in numbers. These numbers were all given. Like there's a 90% probability here that the test is positive when the patient is sick. So this is 0.9. Where do I write it? There's 0.9 here. And there was 1% of the population is sick. So the unconditional one, this is going to be times 0.01. We divide by, well, this is the same. This is 0.9 times 0.01, and then plus the conditional probability that the test is positive, even though the patient is well. This was 10% times the probability that the patient is well. The unconditional one, this was 0.99. So you plug in these numbers and you get that this here is like 0.082. Right, so this is 8.2%. And so what happens is that the unconditional probability of actually being sick before the test was 1%. Now you test positive under these conditions, your probability jumps up to 8.2. So this is just important to keep in mind when you get tested for something, that this test is not perfect. And because it's not perfect, you can test positive. You can test positive without being sick. And here, the conditional probability of actually being sick, given that the test is positive, is 8.2%. So this is one application of Bayes' rule. It is, you're always given the opposite. You're always given like, how often does the test tell you the correct thing? But what you're interested in is the opposite. And so to get the opposite, you need Bayes' rule. And so here's a specific example where you do a calculation related to testing. Like these numbers here are not perfect, right? This is not 100, this is not 100. And it's because they're lower that you get that even though your test is positive, the probability of you being sick in this particular example is 8.2%. And this is quite far away from like 50% or 80% or 90%. When you look at something like this and you think that maybe this is 90% accurate, okay, but it doesn't mean that the probability of you being sick, given that the test is positive, is 90%. To the contrary, this is 8.2. Are there questions on Bayes? This is a basic example of a Bayes rule. It doesn't appear to have much to do with our class, but I learned some years ago that maybe this is not highlighted enough, that you actually need to perform a Bayes calculation if you want to know something about outcomes of testing. And so when you speak to your doctor is absolutely fully aware of Bayes' rule, and so you can talk to your doctor about it, and you can ask, what is this probability actually going to be? Not particularly, if you were to be interested in it, I'm curious about these numbers, of course, but I'm much more curious about, given that my test is positive, what is the probability that I actually have the disease? And these numbers here, you have to ask your doctor to get. Or you have to calculate them yourself. Are there questions on Bayes' rule? I trust that we have all seen some version of Bayes' rule before. If you are not, if it's a little rusty on base wall, then have a look at these problems I put up. There are a few problems of this nature, and they all go through the same line here of reasoning. All that is happening is that we're able to write the probability of the intersection in two different ways. And of course, it has to be consistent. So it allows us to express one conditional probability in terms of the other one. But it's this ratio, this P of A divided by P of B, that thing has to scale everything. Right? So it's insufficient to just know what this number is. If you want to know what that number is, you also need to know what this ratio here is. And this ratio, this can be quite different than 1. Okay, if we're all good on that, we'll go back and start talking about the Radon-Nikodym process and base rule in that setting. So, so what is the? So you have a measure. So back to our setting. So if we have this setting where P tilde is absolutely continuous with respect to P on say F, then what we're interested in, well, we write down the conditional expectation. So we will be able to say that so Radon-Nikodym Radon-Nikodym's theorem gives us this derivative dp tilde dp. So if it's absolutely continuous, this one is positive, it has expectation 1. And it has this crucial property that I can get the probabilities under the tilde measure simply by calculating the expectation of the Radon-Nikodym derivative over this set A. Right? So this here is the expectation 1A dp tilde dp. So we have this random variable. Now this is for all sets A in F. Right? So now we have our filtration. We have our filtration F, and we have this filtration structure. So we have that Fn is inside Fn plus 1, and the all inside F. So in particular, given I have the formula here for all sets in the big one, I will also have it for all sets in the smaller one. Right, so then recall that if I look at Zn to be the conditional expectation of a random variable given Fn, recall that this is a martingale. And maybe we should just quickly use iterated expectations just to recall it. So we're going to say that the expectation of Cn plus 1 given Fn, how would I calculate it? I'll start by plugging in the definition. Start by plugging in the definition. And so now I have the situation where I have Fn and Fn plus 1, these sitting next to each other. Which one wins, the bigger one or the smaller one? Which one wins? I have fn and fn plus 1. When I compute the conditional expectation of a conditional expectation, and I know that fn is smaller than fn plus 1, which of these two conditional expectations will win? So I got fn is inside fn plus 1. I have a conditional expectation of a random variable given 1, and then I compute the conditional expectation of that conditional expectation given the other one. Which of these two here will win? What should I write here? Fn, very good. This will be Fn. And so now we're back. This is the conditional expectation of the Radon-Nikodym derivative given Fn. This is my Cn. So this here gives me the martingale property. And the second thing that we need to know is that if this formula here is true for all A and F, this is true for all A and F. So in particular, I will have that P tilde of A, well, it will be equal to the integral over A dP tilde dP. But now I'm going to restrict my attention to A and Fn. I know by definition of the conditional expectation that this will be the same as integrating the conditional expectation over that set. Right? The conditional expectation has two properties. We recall that the conditional expectation has two properties. One is it satisfies, the first one is that it's Fn measurable. And the second property is that if I integrate over sets in Fn, this is the same as integrating the conditional expectation over those sets. Right. This is for all A in Fn. So that's the property. It's the second property we're using here. And of course, I can write this here as A Zn dP. So a lemma is, in this respect, the lemma says that if I take a random variable, let y be Fn measurable. I need that the expectation of y under the tilde measure is finite. Well then, if I am to compute the expectation of y, this can be simply calculated as an expectation not under the tilde measure, but of y times Cn. Right, so I can calculate expectations under the tilde measure simply by using this Radon-Nikodym derivative process, this martingale. So the way that it works is as before. So we give the proof for elementary random variable. So let's do it for y just being an indicator for a set A and F. We give the proof for these ones, and then to get the general proof, you have to multiply onto constants, and you have to add them up, and you have to take limits, and so on. We'll just do it here for the case of indicators. And then in that case, I'll have E tilde of y. So that's the expectation on the risk neutral measure, under the risk neutral measure of the random variable 1a. So that would be P tilde of a. So that would be, now we use the formula we had up here. P tilde of a, this would be my Zn dp. That was what we're doing up here. P tilde of is at a is an fn, to get this long chain. Then we're almost there because we can write this here as an expectation of an indicator for A, Cn. And then we just recall that what we have here, this is Y. This is my Y, Cn. So that one works. And then you do the extension. We've done that before. So it's a result of this sort. This is what you'll find. This is what you'll find over in these lemmas here, 521 and 522. This here was lemma 521. What it does is it says, here's a way to the way to calculate expectations under a tilde measure. If you know what the random derivative is, you condition on where the random variable is measurable. If it's fn measurable, you just multiply onto c here. So this here allows us to do a few things. It allows us to tie up one loose end that has been hanging for a while. We've been using a property, but we haven't really proven it. So let me try to tie up one loose end. So in the multivariate binomial model, we had a p measure. We had a p measure, and under that p measure, we had these IIDs, coin flips. This would be U and this would be D. And we also had a p tilde, and we have used multiple times that these size, they were also IID coin flips, but instead of p, we would have p tilde, and we have 1 minus p tilde. And we have a formula. We have a formula for this Radon-Nikodym derivative. Where the Radon-Nikodym derivative. So remember the formula for p tilde? What was the Radon-Nikodym derivative? What was the Radon-Nikodym derivative here? We would have what we have Zn. This would be equal to p tilde divided by p to the number of heads, and q tilde divided by q. This will be the number of tails of the time n. Right, so how did we get this? If I look at Z1, if I looked at C1, so I'll have the P tilde, say heads. I'll get that by integrating. I'll get that by integrating heads of Z1 with respect to P. So this here would be Z1 at heads times P of heads. So this here would be Z1 of heads. That would be times P, right? What's our P here? And then this one here would be P tilde. So we get that Z1, if the first coin flip is heads, this is going to be P tilde divided by P. And likewise, we will get then Z1 of tails. This will be 1 minus P tilde divided by 1 minus P. And so what would it be? What would it be if I had Z1 of heads? Well, this would be P tilde divided by P squared. What would it be if I had C1 of heads tails? This would be P tilde divided by P times 1 minus P tilde divided by P. And so in general, you get this formula, right? So here, the number of heads, this is equal to the number of heads in first n tosses. The number of tails, this is the number of tails in first n tosses. So we talked about this before. Here we're just recalling it. So I have a measure P and I have a measure P tilde, and you relate it with this Van Nicolum derivative. And so how can I just say that the IID? We should prove that they are IID. Like, so in general, if I take two random variables, if I have X is independent of Y under P, but that does not, so remember, how do we prove something is independent? For example, you can look at the joint characteristic functions. So you can look at EIAX plus IBY. If I have independence, it means that the joint characteristic function factors in general, if I have independence, this is not going to spill over. This is not going to spill over to independence under P tilde if P tilde is absolutely continuous with respect to P. And these two, just because you're independent under one measure, it may or may not be the case that you're independent under an absolutely continuous measure. You don't have a result like that. Right, so it could be that the joint characteristic functions under the P tilde measure, it could be that the joint characteristic functions under the P tilde measure would not have that property, EAX plus IBY, that this could not be just a product and so when I get to this point, there will always be students that are skeptical. So like, okay, give me an example. Okay, so here's the example that I had in mind for you guys to see is over in the homework. So it's over here in the homework. Here is here's a structure where you have x and y, the independent and the standard normals. Here's a measure, dq dp. This is strictly positive, so q here is going to be even equivalent to p because you have strict positivity. And now you're asking what is the joint distribution of x and y, but under this measure here. And what you'll see is that even though you're independent under P, and even though P and Q are equivalent, it's not true that X and Y are independent under that measure Q. What you see is this theta here, this is going to appear as a correlation coefficient. So if we don't have this property, then we should try to figure out a way to check that we indeed have. So we don't have this, but we're still claiming that in this particular example, if I have my measure P and I define the random Nicodim process according to this formula here, I'm still claiming that under that P tilde measure, I do have these conflicts to be IID. How do I prove that? Are you guys good on the question? I started out my multi-period binomial model saying that I have my conflicts and the IID under P. And we've been working with a model under P tilde. And this model under P tilde, I've been using that the also IID under that measure P tilde that has this particular process as its random derivative. Right, so I should prove this property here. I cannot just both assume that I have a measure P tilde with the IID property and this random derivative. Like these two things, they need to be consistent. And how would one go about proving that? So let me try to show in our setting this actually works. So let us show that psi 1 is independent of psi 2 under this measure P tilde. We have to prove that the entire sequence is, so I'm just going to do a simple case. And then if you want to try to generalize it, you can do that yourself. Let us prove that that these conflicts, are indeed also independent under P tilde, and they're given to be under P. Okay, so the way that it goes is through this lemma we just proved. What we are interested in is showing this property. And so what we do is we'll compute the expectation of EIA psi 1 plus, maybe I should call it, I'll just call it AIB psi 2, and I am under the tilde measure. So what would I have then? So I will use the lemma. This here was the lemma. recall what the lemma said, namely that it says that if I have a random variable that is fn measurable, then if I am to compute an expectation, I can multiply onto the random negative derivative. So there was a question in the chat. Yeah. So the only thing when you talk about the expected value, remember you have to compute. It's not enough to say that it's the expected value of psi1 times psi2. You need certain functions of psi1 and psi2, and then have that be the product. So here I'm taking the characteristic functions. You could have used other ones too here. I like the characteristic functions because they always work. So the lemma says multiply onto this random negative derivative, and then you don't have to compute under the tilde measure. You have to compute under how far up you need to go. This is C2. And then the expectation of IA psi1 plus IB psi2. So then what? Then I'll plug in what is the random negative derivative psi z2. We had a formula. It's this mess here. The p tilde over p times to the power number of heads that we've seen in the first n tosses and the number of tails that we've seen in the first tosses. We're going to have a p tilde. My pen is out of ink. I have a p tilde over p to the power number of heads in the first two tosses. So yes, this is not particularly good notation. Maybe I should write this a little bit different. Yeah, okay. We will follow the notation from before and then change it up a little bit. So we have 1 minus p tilde divided by 1 minus p to the power number of tails in the first two tosses times e to the a psi1 plus ib to the psi2. How do we get from here? How do we solve the problem now? Well, here we'll have the number of heads in the first two tosses. And that's going to be equal to the sum. The number of heads in the first two tosses is going to be equal to the sum of the number of heads in the first toss plus the number of heads in the second toss. So this here is going to be equal to E, and then it'll be P tilde divided by P times the number of heads in the first toss times P tilde divided by P to the number of heads in the second toss minus the number of heads in the first toss. And I'll do the same thing for the next one. 1 minus P tilde over 1 minus P. Number of tails in the first toss times the number of tails in the second toss. And then times this exponential. So what do I do now? Okay, so we have a random variable here, one here, one here, and then I have one here and one here. So I have 6 random variables. How are they related? Well, this one here is related to the first toss. This one here is related to the second toss. This one here is related to the first toss. This one here is related to the second toss. This is the first toss. This is the second toss. And now I am under P. Right, so under P, the assumption is that I have IIDs. So on the P, I have the independence property. So I'll write this here out. I'll write this here out as, give myself some more space. I'll write this here out. This is because I have that psi1 is independent of psi2 under P. And I am computing expectations under P. So then I'll plug in, I'll use the property that I'm independent. So the expectation of all these things, you will factor it. It will become the product of the two. So I collect everything that has to do with the first toss. So that's this guy, it's this guy. And it's this guy. That's everything that has to do with the first toss times everything that has to do with the second toss. The second toss, number of heads in 2 minus the number of heads in 1 times 1 minus p tilde. Same thing for the tails. Number of tails in the first 2 minus the number of tails in the first 1. And then e to the IB psi 2. So now we're almost there, because what's the first part? This one here, this is my Z1. So the first part will be expectation of C1 EIA psi 1. Now the second part is a little bit more tricky, but one thing I can do without disturbing is multiply on to the expectation of Z1, because this quantity is equal to 1. This here is equal to 1. Like radical derivatives, we know that they have expectation 1. This was given all the way up here. So the expectation of the random variable is 1, and this martingale we have here, this is going to inherit that expectation. And so the expectation of the conditional expectation is the unconditional one, so the expectation of Zn is going to be 1. So I can multiply this expectation by a 1, it will not disturb it. And then I can use that C1 is independent of what I have up here, because Z1 only involves the first coin toss, and what I have in here only involves the second toss. So I can combine the two. Again, using independence, you'll use that Z1 is independent of psi 2 under P. Bring them back together, get an expectation of C1 times P tilde over P, number of heads in the first 2 tosses minus the number of heads in the first toss, times 1 minus P tilde, divided by 1 minus P, number of tails in the first 2 tosses minus the number of tails in the first toss, and then this exponential IB psi 2. And then I can combine the first terms, these 2 terms here. This is exactly my C2. So I get that the second quantity here, this is E of C2 times I EIB psi 2. And then I can write it now all back. I use the lemma again. This is the lemma. It says that when I compute expectations of a random derivative times a random variable, I can write this as an expectation where I absorb the radical derivative into a change of measure of e I a sine 1 times, and now do the same thing, the C2 goes into a change of measure. And then I get the independence property because the joint characteristic function factors into the two. So we now have established this was a loose end. It was something that we've been using quite a bit, namely that the coin flips, they remain independent under that measure P tilde. Are there any questions on the calculations that we did here? What we're showing is that the joint characteristic function under this P tilde measure, it factors, this will give us independence, and the thing that we use is we relate expectations under the tilde measure with expectations under the P measure. And the thing that'll take you from one to the other is if I have a random variable that is Fn measurable, that random variable, you can calculate its expectation simply by computing an expectation under the P measure, but you have to multiply out with a radical derivative. Are there any questions on the calculations we did here? It looks a little bit messy, but it's not so bad. The last thing that we need is Bayes' rule in this setting that we have here. The last result that we need is Bayes' rule, and again this is something you'll find over in chapter 5 in a thick book. So we started out with Bayes' rule for simple probabilities, and so here is how we get Bayes' rule for these conditional expectations that we've been wanting. So this is another lemma, and this is what I would call Bayes' rule. So again, you take a random variable, you make the assumption that under the tilde measure you're finite, and you make the assumption that y is this time it's going to be Fm measurable, and then what you're interested in is calculating not the expectations anymore, but you're interested in calculating the conditional expectation. So you pick an m which is bigger than n. So you're interested in computing the conditional expectation, but under the tilde measure. And so it's a little bit different than the formula we had before because there's a conditional expectation now. So before we did not condition. Here was just the unconditional expectation. So now we're computing a conditional expectation. So we're going to get something like this on the right-hand side, but it's going to look a little bit different. It's going to look more like Bayes' formula. What you'll have here is an expectation. So you'll multiply onto the radical derivative. Y is Fm measurable, so you get YZM given Fn, and then divided here by Zn. So we're claiming that this conditional expectation here has that form. So to prove it, we have to verify the two properties of a conditional expectation. So the first one is the conditional expectation has to be Fm measurable. But if I look at the right-hand side, this is Fn measurable, right? Zn is, and here I'm conditioning on Fn. I'm conditioning on Fn. This is going to give me an Fn measurable random variable. And the second is to prove the partial averaging property. You also have to prove that one. Okay, so we have to take a set in Fn, and then we have to prove that when I integrate, I have to show that when I integrate y, I am on at the tilde measure, so this is dp tilde, I'm going to get the same thing as when I integrate what's on the right-hand side. As when I integrate what's on the right-hand side. This is Fn divided by Zn with respect to p tilde. We have to show that this is true, right? The second property that conditional expectations satisfy is that I take a set in Fn, the thing I condition on, I integrate the conditional expectation, or I integrate the random variable y. Regardless of what I do, I'll get the same thing. Okay, so how are we going to do this? So let's work on the right-hand side and show that this is equal to the left-hand side. The integral over a of the right-hand side. This is yzm given fn divided by zn dp. This is equal to, well, it's going to be an expectation. There'll be an indicator for a. There'll be an expectation on the p of yzm given fn divided by zn. Okay, I have to prove that this is the same thing as the expectation of y over the set a with respect to p tilde. So then what I do is I'll use the lemma. It says if I have an fn measurable random variable, I can get the expectation simply by multiplying onto zn, and we see that the zn's cancel out. This was the lemma we had. You relate expectations under the tilde measure. Expectations under the tilde measure, you multiply onto the Random derivative. When you multiply onto the Random derivative, it's going to cancel out the one we have down here. Okay, so now I have 1a. 1a, well, a was in fn, so this is measurable. He can travel inside because he's measurable. And then I'm left with an expectation of a conditional expectation. We know that this is equal to the unconditional one, so this is equal to the expectation of 1a y zm. And that's because conditional expectations are unbiased. Conditional expectations are unbiased. And then we can use the lemma one more time. I now use it the opposite direction. I have an expectation where there's a Random derivative. He can go inside the change of measure, and I get a tilde. I give up the zn, and I put a tilde instead. This is 1a y. Okay, and then I'm done because this is exactly that expectation that I was hunting. So this is Bayes' rule for conditional expectations. It allows us to relate a conditional expectation on the one measure in terms of a conditional expectation of the other one. However, you have to use this Random derivative process in there to get it to work. And a main application of this is to say that if, so maybe this is a corollary. So if I take a martingale, Mn, this is a p tilde martingale, if and only if Zn Mn This is a P martingale. And it's not hard to see using Bayes' rule. For example, if we were to say, so let's do the proof in the downward direction. What I'm interested now is in computing the conditional expectation. Like I'm assuming that I have a P tilde martingale. Now I want to relate it to a P martingale, so I'll compute this. I'll use Bayes' rule. Always use Bayes' rule when we have to calculate expectations on the one measure in terms of expectations under the other measure. What I will do is I need to make it look like this. So I will divide here by, maybe I'll multiply onto Zn and divide by Zn. That didn't change anything. And then I'll use Bayes' rule. So here comes Bayes. This first part here, this is just going to be the expectation under the tilde measure of mn plus 1 given fn times Cn. So this here was Bayes. And then I'll use that m tilde, then I'll use that m was given to be a martingale under the tilde measure, so this here would be mn times Cn. And going up, this is similar. So Bayes' rule, we'll be using Bayes' rule whenever we have to work with dynamics and calculating conditional expectations under these tilde measures. We will use Bayes' rule. And the way that it goes is you need to have this Radon-Nikodym derivative process that will allow you to calculate conditional expectations as well as expectations on the one measure in terms of these expectations under the other. Okay, I think we have a few minutes left. You guys have been very quiet tonight. Are there any questions on what we've been talking about? Are there any questions or comments about what we've been through today? So tomorrow in the TA session, there are going to be problems on how to use this Radon-Nikodym process in a handful of different problems. So you can find some practice there. I also put up a few problems about Bayes' rule, just a basic vanilla one from just intro to probability, and then there are office hours coming up on Thursday and Friday. If there are questions about the material, this will be a good time to talk about it. And then the exams, they will start next week. And so if you have signed up for it, check that I got the right time slot put in. There was one of you that already pointed out that I messed up. So if you send me an email or put it on the time slot, I'll try to fix it. If you haven't sent me an email, try to pick one of the slots that is available. Send me an email, and then I'll update the stuff on Canvas. However, if I don't hear from you, at some point you need to get scheduled, and so I will have to schedule you on my own, and then it just becomes more complicated. So try to use. There are still some slots left on Mondays and Tuesdays. Try to get it to work, and then we can get everybody scheduled. Okay. Are there any questions? You have been very quiet. Okay, then have a good day, guys, and I hope to see you on Thursday and Friday mornings. Okay. Let's see. Can I try whiteboard again? Yes, of course. I'm going to set up whiteboard right now. Yep. Do you see the whiteboard? Yeah, I guess so. We can see writing. And then there was a question about getting scheduled. Oh. Then there was a question about getting scheduled. Have you all played enough with the whiteboard? Okay, so then I'm going to click that one. Rocher, you're asking if you can get scheduled for 9 o'clock on Wednesday. Yep, that seems to work. Yep, that works. Are there more students in here that need to be scheduled or have questions? Okay, I guess not.